Hey guys, Mr. Backberg here. In this video, we're going to look at radioactivity. So as we're talking about radioactivity, when an atom emits some of its mass as radiation, then the remainder of that atom reforms to make an atom of some new element. This process of radiation and change is called radioactive decay. And an element whose atoms spontaneously go through this process we call radioactive. Now, radioactive carbon-14 decays into nitrogen, and radium, through a number of radioactive steps, ends up decaying into lead. Now, experiments have shown that at any given time, the rate at which a radioactive element decays is approximately proportional to the number of radioactive nuclei present. Thus, the decay of a radioactive element can be described by the equation dy dt equals negative k times y. We're using negative because this is a decay example. If our y sub 0 amount is the number of radioactive nuclei present at time 0, the number still present at any later time t can be modeled using the equation y equals y sub 0 times e raised to the negative kt. Now, when we're talking about radioactive elements, half-life is an important idea. So the half-life of a radioactive element is the time required for half of the radioactive nuclei present in a sample to decay. And the half-life is a constant that depends only on the radioactive substance and not on the number of radioactive nuclei present in the sample. So basically what that's saying is that it doesn't matter how big a sample you've got, it only matters what element you're dealing with. So if you're dealing with, for example, carbon-14, regardless of how big your initial sample is, it's going to take the same amount of time for half of that sample to decay. So what we're going to do in this example is using that decay equation, y equals y sub 0 times e raised to the negative kt, we're going to use that to help us find the half-life of a radioactive substance, and we're going to show that the half-life only depends on that decay constant k. So as we're looking at this equation, we're talking about the half-life of a substance, and that means how long it takes for half of your sample to decay away. Now remember, this y sub 0 means your initial amount. So what we're hoping for as we're looking at this equation, y sub 0 e to the negative kt, is we're looking for half of our original sample to decay away. So we want to end up with half of that initial y sub 0 amount. And now what we're going to do with this equation is go through and solve it for t, and we're going to show that t only depends on what that k value decay constant is. Now I guess what I notice about this equation that we just wrote is that we've got y sub 0 happening on each side. So what I'm actually going to do is divide both sides by y sub 0 to get those to cancel out. So then my equation says e to the negative kt equals 1/2. Now I said that we were solving for t, and right now we've got a little bit of an issue because t is up as an exponent on that e. So in order to cancel out that e, what we're going to need to do is take the natural log of both sides. Then the natural log will cancel out with the e, and we'll just have the negative kt on the left-hand side, and then on the right-hand side we're going to have the natural log of 1/2. Now our goal is to get t alone, so to get rid of that negative k attached to the t, I'm just going to divide that over to the other side. So we're dividing both sides by negative k. So then what we end up with is an equation that says t, or the time, is equal to the natural log of 1/2 divided by negative k. Now there is just a little bit more manipulation that we can do with this. If you've got the natural log of 1 over some number, then you can change that to being the natural log of just that number, but you need to make it negative. So we can actually rewrite the numerator here as negative natural log of 2, and then if we're dividing that by negative k, then this double negative in there is going to turn positive. So for our final answer, we're going to say that our t is equal to the natural log of 2 divided by that k value decay constant. So this t value represents the half-life of whatever element it is that we're dealing with. And we can see that it only depends on that k value. And the initial amount, that y sub 0, doesn't show up anywhere in our resulting equation. So like we mentioned before, the amount of sample that you start with at the very beginning does not matter. It will always decay at the same exact rate. So summarizing what we just did, the half-life of any radioactive substance with rate constant K, we can say that its half-life is the natural log of 2 divided by whatever that K value is. That's going to be it for this video. Thanks for watching.